Hi, welcome back. Okay, so this episode I want to address a question that my friend Casey sent in that is actually a really good question and doesn't get addressed that much. So we're going to talk pretty quick. We're just going to talk about some cool science, how science works in space, and hopefully that will clear up some things for some of you who may have had a similar question. So the question that Casey asked me was, why is everything flat? We look at our solar system, it's flat. You can see planets with their moons, and they're sort of in a flat plane. Our solar system is all on a flat plane. And when you see galaxies, a lot of the ones that we see are spiral flat planes. Is our universe flat? Is everything flat? Is it all one flat sheet? What's going on? There's a few things to unpack there, and it's a really good question. Basically, what it comes down to is angular momentum and conservation of angular momentum. Now, when things spin, if you study physics, you talk about the right-hand rule a lot, and you talk about rotational forces, and if you use your right hand, there's a force component that goes in the vertical direction when we talk about rotation. And this plays an effect in objects. So you may have seen experiments with, where we talk about figure skaters when they're spinning, they bring their arms in and they start to spin faster. This is all tied with that concept. Now, in space, there's a lot of gas and dust floating around. So we have these clouds of dust and gas, and I'm going to talk about star systems first. So before I continue, if you've not watched the cosmological address and you don't know what I mean when I say kind of the difference between star systems or galaxies or the universe, I would recommend you go watch that and then pop back here. All right, so welcome back if you went on an adventure, and we'll get back into it. So when we talk about star systems developing, we typically talk about these nebulas that are protostar nebulas. There's a lot of hydrogen, a lot of dust, a lot of gas. And what happens is you have these dust and gas clouds that are floating out there, and the particles are colliding into one another. And sometimes when they collide, they stick to each other and get bigger, which gives them a tiny amount of gravity, enough that another sort of dust cloud or dust particle will drop by and stick onto that. And we talk about a snowball effect. But you can imagine as these particles start to clump together and get bigger, things are going to collide into them, and they're not going to hit perfectly straight on. They're going to sort of graze on the side and maybe induce a spinning motion. And so as you have these big cloud particles sort of interacting with each other, they start to clump and then they start to spin, and there starts to become an overall rotational component to this cloud. And as it starts to rotate and filter out and go into these different chunks, it starts to flatten due to angular momentum. And so as it's flattening, you have the middle of this dust cloud is starting to get hotter and hotter because of everything colliding into it, just from friction. Imagine rubbing your hands together. It's a similar thing. Your hands get hotter. All these dust and gas particles start to get hotter and hotter and hotter in the center. And eventually they reach a mass and a friction and a temperature that ignite a star. And so you have a star born, but then you still have a bunch of dust and gas floating around there. And so as this is all rotating, it all starts to flatten out, and you get this big, long, flattened system with a star in the middle. And then you're flattening out, and all of this, you have your star, and all of this dust and gas is still floating around, and it starts to break off into chunks because you have some bigger and some smaller. And as it's rotating, things are getting flung into each other. And then that's kind of how we get planets from that. So the same thing happens on a micro level. If you have a big gas giant that starts to form, it's also going to have these gravitational pull of particles that are all starting to spin around it, and they're all going to sort of flatten out. Now, we don't see this 100% just because of the scale, and because moons with planets don't necessarily all form at the same time. And even planets in star systems don't necessarily form at the same time. They can be captured. So one of the things that you can study in astronomy is if you see a star system where everything's really flat, but you see one object that's maybe rotating at a weird angle, but it's still kind of at the same distances, then you could kind of possibly say that maybe it was captured. Yeah, there's a lot of clauses in what I'm saying there. it's because we're studying it. We don't necessarily get to see this all happen live. We see chunks of it in different parts of our galaxy. And but if something's coming in at a weird angle, you can say it was probably captured. Now, we do also have objects in our solar system that have huge radiuses. They come in from huge distances, typically comets, and they come in at weird angles. They're coming in from the Oort cloud, which is the furthest out part of our solar system, where you just have a whole bunch of rocks and dust that never really got pulled into that original sort of spinning component to flatten into our solar system. Now, there's a lot to unpack there, so feel free to hit me up if you've got any questions about what I said. I'm more than happy to go into it in a future episode. But the same thing sort of happens with galaxy evolution. Galaxy evolution is a whole other part of astronomy that people study. And again, because we're not able to see it all happen in one go, we see different components of galaxy evolution happen in different galaxies. We see these different stages and we have to piece it together like a puzzle. And so when we talk about galaxies, we're talking about islands of stars is the old poetic way to classify galaxies. But they can be round, nebulous, what we call elliptical galaxies, or they can be flat, spiral galaxies. And then they have their own little classifications within that. But essentially what happens is you can picture big clouds of stars crashing into each other. Things move in space, and if they collide or go past one another, what's going to happen is you're going to get all these particles sort of interacting, and they're going to start spinning around, and eventually they're going to flatten out, and you're going to get a spiral galaxy. Now, like I said, this is a general explanation for what's going on. There are a lot of nuances. There's lots of fields, people trying to study this to figure out exactly what's going on. But it's interesting to think about, and we can build simulations that are fairly basic, just using the force of gravity, as a way to demonstrate that when you have these big clouds of particles that start spinning or colliding into one another, you end up with those particles all sort of moving in a flat shape. Now, the last part of Casey's question was, what about the universe? Is our universe flat? Yes, but in a different way. So remember, our universe is everything that we're talking about. So when we talk about solar systems or galaxies, we're talking about dust and gas particles that are in clouds and forming and running into each other. Our universe itself encompasses everything. So to that extent, angular momentum isn't really what's making our universe seem flat. As far as we know, it's flat, but it's flat in a different way. This is a whole other field of cosmology. If you're interested in it, I can do another episode, so let me know about it. We can go into the shape of the universe. But like I said, that it's kind of different from this whole aspect of solar systems and galaxies being flat. So Casey, I hope that answered your question. And for those of you who had the same question, I hope it answered yours as well. And again, I love questions, so keep them coming. All right, thanks for watching. I'll catch you next time.